Hello and welcome to the channel. Today we'll be going over a simple BJT emitter follower configuration by making an analog DC motor control circuit and highlight some common mistakes you need to avoid while you try to drive a high current load from a low power source. For instance, say you picked up a cheap 5-volt DC motor from Amazon and thought to yourself, hey, I could power this with my Arduino because it outputs 5 volts. Wrong, don't do that. The reason this is bad is because DC motors, especially these small cheap ones, have very low resistance, often in single-digit ohm values, which means when loaded, this 5-volt motor could source 5 volts divided by 5 ohms, a whole amp. This could burn up your MCU. Now let's talk about what will be used in this video as a demonstration. Behold, the 12-volt DC motor from Amazon. While the stated specs of this motor are a work of fiction, probably hallucinated by a drunk man somewhere between Shenzhen and a shipping container, as engineers, we don't let that stop us and take some simple measurements that show this motor has a resistance of 8 ohms and has the potential to demand up to 1.5 amps because of its rated voltage at 12 volts DC. We need a circuit to buffer that current. We will control this DC motor using an analog style potentiometer with a TIP41C NPN power BJT in an emitter follower configuration, also known as a buffer. Now you may be asking yourself, why use an emitter follower configuration here? And that's a great question. That's because one of the main functions of the emitter follower configuration is as a current buffer. The emitter follower configuration allows a tiny current through the base while sourcing large current through the collector. This means that the voltage stays nearly the same while the current you are able to source becomes much larger, and as you know, high current is much more dangerous than high voltage. So this separation between control and power circuitry becomes very important. A more technical way to describe this current buffer is to say that it has a very high input impedance, meaning it will draw very little current from sensitive electronics like an MCU, all while maintaining a unity voltage gain, which is just another way of saying the gain is equal to 1. With all that said, I do need to mention that the emitter follower is not without some drawbacks that are worth mentioning here. First one being, this simple configuration will drop voltage across the base to emitter, meaning that the DC motor will see about 11.3 volts due to the 0.7 volt drop instead of the 12 volts that we really want, which would be a unity voltage gain of 1. The second drawback, it's just not the best method. Plain and simple, using a MOSFET combined with PWM would increase efficiency and torque at low speed as well as reduce power losses. However, using a BJT is typically cheaper and simpler for basic control. As a quick safety note, when working with large inductive loads like electric motors, always be mindful of back EMF or back electromotive force. When the mag field around the inductor collapses, it sends a transient voltage spike as well as current back across your circuitry and will fry small components like transistors. To prevent this, a simple method is to add a flyback diode in parallel with the motor. This will create a decaying oscillator as the back EMF recirculates through the motor, expanding the mag field, and the mag field collapses again, and the process repeats. Now that we won't accidentally fry our control circuitry, let's figure out how to control the current going into the base. First, we need variable control, so we will use a simple potentiometer that will act as a variable voltage divider. What's important is that the potentiometer will be able to turn off the motor as well as provide the maximum current this motor is capable of drawing. It's important to note that potentiometers go to 0 ohms, which would cause a short in our circuit and send way too much current through the base. In order to fix this, we will place a limiting resistor called RB before the base to ensure the base current does not exceed what we need. With our design requirements all identified, let's now calculate what size components we need in order to make this happen. The TIP41C is a power BJT, meaning it has a lower beta value and can handle higher currents than the small signal BJTs we worked with for the common emitter video. Recall that beta equals the current in the collector divided by the current in the base, beta being synonymous with HFE. We can see that the minimum value is 15 on the datasheet, so we will calculate our base current using this value. Because the motor can source up to 1.2 amps, we calculate IB, or the current in the base, to be 80 milliamps. Now, as an electronics designer, we never want to be right at our maximum or our minimum. So on the off chance that the motor requires even more current, we will multiply our current in the base number by 2 to get 160 milliamps. Now that we know 160 milliamps is the maximum possible current we need through the base, we can choose our resistor for RB by using Ohm's law. First, we take our source voltage 12 minus VBE on, which is the voltage drop across the transistor, divided by the current through the base, and that gives us about 70.62 ohms. Now, being in the real world, 70.62 is not a real value, so we will size that down and choose 47 ohms. The next step is to choose the correct size for the potentiometer. Remember that when the potentiometer is at its minimum resistance or shorted, the RB, or base resistor we just calculated, will be able to provide max current to the base while limiting the current through the potentiometer so it doesn't burn out. With that in mind, let's calculate what resistance value would be ideal for the potentiometer while having fine control over the speed of the motor. Due to the very large resistance of the pot when fully turned, it will dominate control of the base current, which means that the current limiting base resistor RB becomes negligible, so we won't include it in our final calculation. Now let's draw out some pot values and see what we get. First one being a 1 kilo ohm pot. As we follow the current path, we will end up with 11 milliamps as the base current. Similarly, when we use the 5 kilo ohm pot, we end up with 2.2 milliamps going into the base current when it's off, and this is much lower. We will choose this as our ideal pot for the situation. Another reason why this is ideal is the 5 kilo ohm pot will provide a much smoother voltage division as it's moved than the 1 kilo ohm pot will. Slight hand tremors or jerky motions will not be as evident using a 5 kilo ohm pot than it would be using a 1 kilo ohm. With all that out of the way, we are ready to build our circuit. So let's go ahead and take a look at what happens. Alright, this is our setup. We have a diode in parallel in the back of the motor here. And then in the middle we have our main circuitry, and on the right we have a variable control. All this is just a potentiometer with some wires soldered onto the back of it. So let's turn on our power here and get going. Now watch the current closely as I twist this potentiometer here. You can see it got up to about 250 milliamps before it even began to turn. And that's because of the gearbox on this motor. It's providing a lot of static friction that needs to be overcome. And this is a common issue with motors that are first starting. Now I'm turning it down. You can see the speed begin to decrease. Our current is also going down as well. And here I just turned it off. Well, I hope you learned something. Stay tuned for the next video.